Hello, I'm the speaker and the first author, Hyunjun Choi. In this paper, we identified the limitation of the existing approaches that utilize auxiliary data. The issue is that, as seen in the blue box, they assign the same loss to all outlier data. Why do we need different regularization losses for outlier data? We conducted inference on outlier data using the pre-trained network in semantic segmentation task. As you can see, the graph shows irregular patterns. Existing network exhibits class-specific struggles rather than a uniform confusion across classes. To handle this issue, a loss I propose is a modified version of the previous energy loss. The key difference is that shown in the red box, it provides the adaptive loss for outlier data based on the parameter z. We verify effect of unknown loss in three following tasks. This is our qualitative result for semantic segmentation task. Okay, let's start more detailed presentation of our paper. I'm currently a PhD candidate in electrical engineering at Seoul National University, conducting research in perception and intelligence laboratory. This work was done during my internship at Light Flux Incorporation. Previous research on OD detection can be broadly categorized into two approaches, observer and mutator methods. The observer approach does not directly intervene in the training process. The mutator approach, on the other hand, actively intervenes in the training process. Among these mutator methods, I paid attention to the approach that utilizes additional data. This approach improves OD detection performance by utilizing additional data in training. Auxiliary data consists of classes that do not overlap with OD test data or indecision data. There are papers related to this methodology in the context of image classification task and for semantic segmentation task. In the ICLAIR 2018 paper on OE outlier exposure, they were the first to utilize auxiliary data as outlier data in training. This approach demonstrates significantly better performance compared to the traditional MSP model. The key method involves incorporating a regularization loss for outlier data into the fine-tuning process. The loss can be broken down as follows. The left side corresponds to cross-entropy loss for conventional classification, while the right side represents the leverage of the OE loss. The OE loss aims to enforce outlier data to be closer to a uniform distribution, resulting in a cross-entropy loss with respect to the uniform distribution. The subsequent paper, Meta-ORI, applies this OE loss for OD detection in the context of semantic segmentation. Another paper is Energy OE, published at NIRIPS 2020. First, instead of using MSP score, they propose a new measure called energy score. It is obtained by applying lump sum expenditure to the losses, which are the values before the softmax operation. They leverage a regularization loss for the new energy score during the fine-tuning stage. The proposed loss is a double hinge loss for energy score of both in-distribution and out-of-distribution samples. Although the introduced loss adds more hyperparameters and complexity, it demonstrates improved OD detection performance compared to previous OE methods. Similarly, the Pebble paper presented at ECCB 2022 applied this loss to the problem of semantic segmentation OD detection. However, the existing OE and energy regulation loss method have identified a problem. The issue is that, as seen in the blue box, they assign the same loss to all outlier data. Why do we need different regulation losses for outlier data? We conducted inference on outlier data using pre-trained network in semantic segmentation. As you can see, the graph shows irregular patterns. Existing network exhibits class-specific struggles rather than a uniform confusion across classes. To handle this issue, loss I propose is a modified version of the previous energy loss. The key difference is that, as shown in the red box, it provides an adaptive loss for outlier data based on a parameter z. Increasing z corresponds to a stronger regularization, and the weight of the subsequent z values represent their importance. This is our new balanced energy regularization loss. So you have to understand what z term means intuitively. It can be seen as an indicator of whether the sample belongs to the majority classes. Z, as seen in the final equation, is the sum of product of two probabilities. The left side corresponds to posterior probability, which is the softmax output of the existing network. Then, on the right side, there is the new prior probability obtained through inference on the pre-trained outlier data. The graph shown earlier can be seen as a representation of this prior distribution. The proposed loss assigns higher z-values to outlier samples with a higher probability of being confused by the existing model, thereby providing stronger regularization for such samples. The training process can be summarized as follows. In step 1, we utilize the existing pre-trained network to perform inference on outlier data and obtain the prior probability. In step 2, based on the calculated prior probability, we employ our proposed loss functions for fine-tuning. We verify the effect of our novel loss in the following three tasks. This is our qualitative result. For semantic segmentation task, we achieve improved performance compared to the original pattern algorithm. This is our quantitative result. In fish escape test that we can achieve improved performance compared to the original pattern algorithm. We compared our algorithm with Pebble, basic energy OE, and our balanced energy OE on the fish escape validation set and load anomaly test set. Our method consistently outperformed energy OE in terms of performance. In the context of long-tail classification, our method not only outperformed energy OE but also exhibited superior results compared to existing methods. We observed a similar trend in long-tail CVPR 100, where our method showcased comparable improvements in performance. Lastly, in balanced datasets such as CVPR 10 and CVPR 100, we observed a marginal but good improvement in performance compared to energy OE approach. In summary, we proposed a new balanced energy regulation laws, and we showed the effectiveness of our novel laws through extensive experiments.